In this problem, I want to show you something that's actually pretty straightforward to do. Here we have some NumPy data, and we want to work with that NumPy data in order to identify certain patterns within that data. In this problem, we want to find closely grouped values in a numpy.ndarray. Let's take a look. Let's say we have some data, and that data could represent anything. You can see this problem's a little bit more abstract than other problems that we'll look at, and we want to just figure out what are the 3 numbers that are the closest within the data set. And so, for example, if we see 3 sequential numbers, then, well, what we might want to do is pick those 3 numbers. Or if we see 3 numbers that are only 2 apart, but everything else is much further apart, then we might want to choose that. If you think about this from an algorithmic perspective, it should be fairly straightforward how we might go about solving it. Let's take a look at a little bit of background in theory. Algorithmically, the approach that we might want to take to solve this problem, again, not too tricky. What we probably want to do is maybe take the cost of sorting the data and just look at windows of size n. Because if we sort the data, we can say, oh, you know what? It's really easy to pick out that, for example, these 2 values are adjacent or some other values are different. And maybe if we look at every overlapping window of a particular size, then we can just identify which of those overlapping windows have the smallest difference in the sizes from the smallest element to the largest element. When we talk about overlapping windows of a particular size, well, that brings to mind something that you've seen me do over and over again, the itertools construction of the nwise function. Very similar to itertools.pairwise. Itertools.pairwise was added fairly recently in Python, and it gives us the ability in pure Python with pure Python data structures to look at some iterable in overlapping pairs. Nwise is my construction that expands upon itertools pairwise and gives you the ability to look at some structure in arbitrary windows of some size. So here, let's do something very similar to pairwise. We'll default to windows of size n, and it just uses a very simple trick that'll make a lot of sense when you think about how this works in something like NumPy or pandas. But here we go. We'll slice some generator from some index to the end for each one of these, enumerating and t'ing each one of the generators n times. And so our nwise should work identical to this pairwise. We just got to add in a missing in there. And you can see, there we go. Except our nwise has the ability to also do windows of size, whatever. Now, if we're working with NumPy data, we probably do not want to use this pairwise or this itertool or this nwise construction. Why? Well, clearly, whenever we're using the itertools module, we will be crossing that restricted computation domain. We'll be iterating over the raw data, and we'll be pulling them out of that boxed layer into the universe of Python data. And it's going to be slow, and it's going to be clumsy, and it's going to require a lot of memory allocation. So the trick is, how do we go about doing something very similar to this pairwise or this nwise, but staying within the restricted computation domain? Well, the trick to this just comes down to understanding what NumPy really is. If we have a NumPy.ndarray, and we look closely at what that ndarray actually is under the covers, well, we'll see that an ndarray is really just an interpreted view of raw memory. When we look at this 1, 2, 3 structure, we can see that really it's just some raw memory at this memory address. In fact, I can even print this as though it were a memory address in hex format. It's just some memory starting at this point with some particular shape, some overall size, so some number of bytes associated with it, some interpreted D type associated with it. Here we're going to assume that this is int64, and some striding. And when we think about what each of these components mean, well, obviously the shape, that kind of makes sense. You know, if I say there's 4 elements here, I can even update what the interpretation thinks the shape of this is. So I can say, oh, it's not 4 values in a row, it's a 2 by 2. Or when I think about the D type, I'm just interpreting what those bits mean. So I could say, oh, it's not int64 data, it's int8 data. And now I have 4 times as much, or I have 8 times as many elements, and you can see the endiness of the machine here as well. Well, what the strides represent, and they represent how we move through this structure in terms of how many bytes we skip to get to the next row, the next layer, the next element. When you think about a numpy.ndarray, especially a multiple dimension numpy.ndarray, well, you got to think it's got to be stored in memory linearly, because Memory ultimately is linear. It's from some address to some other address, and we got to lay this out. And if you remember back to the Fortran days, you might even think, oh, there's different ways that we could take some memory and we could lay this out in order to represent, say, a two-dimensional structure. There's the column ordering, there's the row ordering, there's the Fortran native ordering, there's the C native ordering, the column major and the row major ordering. And of course, NumPy draws from the C default. NumPy by default gives you these row major data. Each row is contiguous in memory, and then each column is after that. And so if I look at this structure and I look at the strides, I can interpret these strides in terms of all of that. I can interpret this in the following way. To go from 0 to 1 on the first dimension, I skip 16 bytes. To go from 0 to 1 or from 1 to 2 on the second dimension, I skip 8 bytes. And so that means that in memory, this one row of the data structure and this one row of the data structure are 16 bytes distant. Well, kind of makes sense. If I'm storing each row contiguously, 16 bytes represents the size of that row. And for a given row, to go from this element to this element forces me to skip 8 bytes. Well, that makes sense because it's in64 data by default, and so that means I'm just skipping one piece of data. If I change the D type to in8, then I would expect the striding to change as well. I would expect me to be, let's not do a reshape here. You'd see, and let's then do a reshape. Let's reshape it first and then do that. And then you can see here, the second entry in the striding is 1. I skip 1 byte to get to the next item. Or if I reshape this even further, you can see I need to reshape this, do it like that. Oh, it's -1 here. Here, if I reshape this into a 3-dimensional structure, a 16 structure, you can see to get to the next row, to get to the next level, you skip 16 bytes. To get to the next row, you skip 8 bytes. And to get to the next column, you skip 1 byte. That's what the striding is all about. Well, it turns out that NumPy allows us to cheat. And what I mean by that is, in NumPy, we can tell it to reinterpret this data by reassigning to the .d type, by reassigning to the .shape, and also we can't reassign to the strides directly because you can imagine that some striding may no longer be consistent with how the underlying data, what the D type is or what the shape of this is, but we are provided with the ability to create a new wrapper layer with any arbitrary striding. And this is one of the parts of NumPy that actually comes up surprisingly often when you want to answer questions like looking at a sliding window. In NumPy's lib stride tricks, you have an as-strided. And the as-strided allows you to take an arbitrary numpy.ND array and to change the striding of that array to say, oh, to get to the next element, you skip not 16 bytes in the original, but maybe 8 bytes. The striding does not have to be consistent with the underlying size of this data, so you can use as-strided to do some weird things like mutate raw memory, and it doesn't necessarily have to be consistent with what the original view of how much data there actually was. Let me show you what I mean by that. If I have a numpy.ND array, and that array has 4 elements in it, and I take this data and I say, okay, take this thing and reinterpret it with some new striding. And the striding I'm going to choose looks like this. We're going to take x's, and we're going to say the new shape is whatever x's original shape was, -1. Yeah. And then we're going to say, we're going to actually make this something like this. We're going to say it's whatever the original shape is, -1. And we're going to add another dimension here of 2. And then I say what the striding is. The striding is whatever its original strides were. And, yeah, that's right. Whatever the original strides were. And then here I want over the size of the original strides, whatever the original strides were. Yeah, like this. Then I should be able to get a structure which gives me windowed views. Because what I've done is I've told NumPy when you skip to the next row here, you're not actually skipping the entirety of all of the elements on that row, you're just skipping one element. So what NumPy has done is, without making any copies of this data, it said, oh, I'm just a structure where to get to the next row, you skip one element worth of data. And so you can see it gave me a windowed view where each one of these rows is just what happens when you slide this window across. And in fact, it's not too hard for me to generalize this. I could do something like this, def rolling, take some array and some size, and it's just an as strided, where I take the original array, and just to copy what I had here, I take the shape, the original shape, I do something like that, to get what the new outer layer is. That gives me one entry for each one of the rolling windows I have. The rolling window size gives me one more entry, and then I take whatever the shape originally was and stack it on here. And then for the strides, I just take whatever the size of one entry was attached on to what the original striding was. And so, if I did this correctly, I should also now have the ability to do arbitrary rolling windows of some arbitrary size. We'll make this a keyword-only argument. There we go. So now I can do windows of size 3, or if I made this larger, windows of size 5. And you can see my code here maybe needs to be aware of what happens if the striding is too big, but windows of size 5, you can see I have rolling windows of size 5. In fact, this is such a common thing that you might want to do that this has even been added to stride tricks. Sliding window view gives you a 0 copy sliding window view of some numpy.ndarray, just by doing some kind of stride tricks. And here, its keyword argument is not size here, but there you go. And so, to take a look at the answer, well, it's actually fairly straightforward. All I want to do is take my original data, sort it, take a look at a sliding window view of this, stride tricks, and perform some broadcasted operation down those windows, staying within the restricted computation domain, and then minimize across that. So I'll take my sorted data, I'll get a sliding window view of the size of the number of elements that I want to identify. So here are 3 elements. I have made no copy to this data, so if I look at the array interface, or actually if I look at shares memory from NumPy shares memory, I should see that the original data and this window view actually share memory because it's just a view of the original data, so that's good. And here, I just have to do a difference on this going down, and so how would I do that? Well, I want to find the difference between all of these elements. That's a little bit ugly, so here, if I want to find, if I do something like this, this gives me all the first elements, this gives me all the second elements, this gives me all the third elements. So, I could do something like take this, here, we'll do our windowed view, gives our windowed view here, and then take that minus the windowed view, all these elements, minus the windowed view, all these elements. So that gives us the difference between these elements, where the last one should be always larger than the first one. And then if we take that and then compute the absolute value of this, that gives us the total distance between the elements. So we can see probably right around here is where our closest values are. So let's just check that. So here, let's see, these are our values. That's our sliding window view. Let's think. We did this a little bit wrong. That's the difference between the first pair, and then we want the difference between the second pair. And the difference between the second pair would look like this. We want to sum up these differences. And let's do the abs. Abs should happen at the very end of this. So this is what we wanted to do. Of course, we can rearrange these operations a little bit. So now if we look at it, it's a little bit more sane. Here we have 4. So about here is where we'd expect to see, somewhere around here is where we'd expect to see the minimum difference between these elements. And let's just double check that so we have our window, very good. And where is that actually minimized? It's actually minimized. Let's make sure this thing is shaped correctly, because this should be Oh no, it's not here. It's right here. It's the 4 between this element and this element, and then 0 between those two elements. Those are the closest values. And once we do that, we just have to figure out where that is in our structure. So we might do an argmax, or an argmin in this case, on this result to figure out what is the index in the original structure where the minimum occurs. And then, there we go. We just have to go to that location and 2 past that location. Or actually, 2 past the location like that. Those are the closest values. And the last step we might do is we might do a little bit of optimization on this. If we look at this arithmetic expression, we can see that for the most part, the left-hand side should be larger than the right-hand side, so we don't need to do an absolute value here. And here, I don't think we need to do an absolute value there either. And then here, we don't actually have to do that subtraction because that'll cancel out. So ultimately, I think we just have to do that difference. And for that difference, what we could do is we could, so this is one thing that's a little bit ugly to do in NumPy, to do the difference operation rather than, say, the sum operation. So what could we do? I'm not sure if this would be any faster. We could, of course, just try and select these 2 values, and then do a broadcast of sum. I don't know that this is actually going to be any better than what we had before. So we could do something like that, and that gives us those values. And then do something like multiply this times, say, 1 and -1, and then do a sum. NumPy, I don't believe, provides us with... Oh, actually, let's see if the diff works. I don't know if this is actually any better than what we had before. Yeah, I guess so. And then get the absolute value of the difference. Or actually, it wants to compute the difference the other direction, so here. And then do that. So I guess we could do that to clean it up a little bit. And then here, we're going to say numbers of this index. Like this. And the index plus whatever the window size was. And there we go. And then we're going to slice from there to there. There we go. And of course, since this is an open interval, we want to grab one more value past the end. But you get the idea. I don't know if that diff really improved anything, but you get the general idea here. And it really comes down to push the operation into the restricted computation domain. Whatever you do, try to avoid pulling the data into Python. That's where something like this is going to become very, very slow if it's not 100 values we're looking at, but say 100 million values we're looking at. Here, this should still be relatively efficient insofar as I can perform any operation efficiently on 100 million values. Maybe if I do 1 million values, you might be able to see. You can see it actually comes pretty close. Of course, the range of these values is quite low, so let's make this even larger of a range. But you can see it's still relatively efficient here, whereas if I were to do this with, say, a n-wise operation, you'd expect this to be significantly slower because we'll be pulling everything out of the restricted computation domain. When we deal with NumPy, these are the kind of tricks that we need to do. We need to be able to play with the strides, play with the d-type, play with the shape in order to do cheap zero-copy views of this data. Sliding window view is just one example of it, but you can construct it yourself via numpy.libs stridetricks.asstrided. Whatever the case may be, this is what you should keep in mind whenever you're trying to solve a problem like this in NumPy.